Hi, I'm Jacob. I work at Rokt on the data infrastructure team. That includes running things like our Kafka on Kubernetes setup. We're currently setting up a NoSQL database on Kubernetes, and as I'm going to talk about today, our experience setting up Spark on Kubernetes as well. So just to talk about Rokt to start with, Rokt is an e-commerce platform that allows e-commerce companies to drive more value during the transaction. We offer a suite of products to e-commerce platforms, including tailored upsells, payments marketplace, and relevant post-purchase offers to end consumers, driven by AI and machine learning. So what I want to talk about today is Rokt's journey, or it's in progress, but how we're migrating our Spark jobs from EMR onto Kubernetes. So right now, we leverage Spark pretty heavily, and we have been quite heavy users of AWS EMR. We've been running about 500 jobs a day at any particular point in time between 250 and 800 nodes on EMR. We have a combination of different jobs, but for the most part, our data is reading from an S3 data lake using Iceberg or Redshift data warehouse. There could be some other data stores sitting around. I don't have full visibility across the platform, so ask some of my colleagues. I'm sure there's some other data platforms out there, but for the most part, I believe it's just Iceberg on S3 and a Redshift data warehouse. We have a combination of batch and streaming jobs with various resource profiles. So we have streaming jobs that run all the time, that scale up and down with our traffic patterns. We have, kind of fortnightly batch jobs that spin up, 40 terabytes of memory and shut down and don't run for another 2 weeks. So we have a lot of different varying workloads, and they're submitted from a lot of different places across the company, notably including Airflow and Kubeflow. But I'm sure that there are some other places that Spark jobs are run from as well. And for the most part, we also spin up EMR clusters on demand. We're not using shared clusters on EMR. So just to talk about some of how EMR powers what we do at Rokt. So EMR powers a lot of our data engineering workloads and machine learning model training. We use it for our MO workloads like TensorFlow, PyTorch, scikit-learn. And we're also using it for data preprocessing and feature engineering. So I guess unlike Canva, we haven't gotten rid of Spark. We're quite heavy users of Spark. So just to talk about kind of some of the goods and bads of our current EMR setup. EMR is obviously easy to use, right? You just one API call to create a cluster, you add your step, and you wait for it to complete. You don't have to worry too much about the underlying infrastructure. Obviously, you still need to, provision your roles and your accesses and, add any appropriate dependencies that you need. But EMR plays pretty well out of the box with existing AWS services like Hive and Glue, or like Glue. EMR also provides us a single pane of glass to see what Spark jobs are running. So we can just, do an EMR API call or go to the AWS console for the region and check what jobs are running on EMR. Slight downside of that, the EMR front page is client-side paginated, so it's a bit hard to scroll through all the jobs, considering that we run 500 a day. But that's just a funny side point. Obviously, on EMR, AWS pre-packages their version of the Spark runtime, which includes a lot of dependencies that you would need for running on AWS already. And they also have their own performance improvements in the runtime, including things like EMRFS to read from S3, I guess in a more efficient way than the open source version. And you also get one-click integrations with common Spark adjacent components that you would need, like Ganglia or the Spark history server. Some of the cons of our current EMR setup, it's hard to implement governance on both the infrastructure and at a data governance level. It's also hard to roll up metrics across jobs. You can look at, the container metric, or you can look at the Ganglia metrics for each job individually, but we found it hard to roll up metrics across jobs to get a view of, for example, whether our jobs are efficient or not across the company. Obviously, on EMR, you pay the price to use EMR. There's a 10 to 20% overhead compared to just running it bare metal yourself on EC2 or ECS or something like that. And you also, we've noticed 5 to 10 minute start times to start up an EMR cluster or to, scale out a cluster as well. This has been a pain point for teams in the past. And I think it stopped us from scaling jobs more efficiently. There's a lot of, from what I understand, there's a lot of kind of static job sizing going around. So we can probably more efficiently, well, we have been utilizing dynamic scaling more efficiently when you can scale the cluster more quickly. And it also doesn't fit with Rokt's cloud agnostic strategy. So which we, at Rokt, we try to use open source technologies that aren't locked into any one particular vendor. And obviously EMR doesn't play as well with this. So at Rokt, we run quite a robust Kubernetes setup already. I think last I checked, we run something like in the multiple tens of thousands of containers in production, or maybe across all environments, kind of day to day. So we're already pretty heavy users of Kubernetes with a robust multi-region Kubernetes setup on EKS. There's a lot of infrastructure as code, CI set up for this already, so we're not new to Kubernetes. We run a lot of our existing backend machine learning platform. We run a lot of things on Kubernetes already. So moving Spark to Kubernetes isn't like a new concept for us. But when we've been looking at moving to Spark and Kubernetes, the obvious fit for running Spark jobs on Kubernetes is the existing Spark operator by Google. So for anyone who's not terribly familiar with Kubernetes, Kubernetes is obviously a way to run containers. An operator in Kubernetes is a way to run, or is a way to specify kind of non-container resources to run. So like this example on the right here, you can specify a Spark application definition, similar to a spec that you might submit to EMR, and the operator will take care of translating that to containers behind the scenes or whatever other resources that the job needs. So like I said, running Spark on Kubernetes fits well with our cloud agnostic strategy. So we could theoretically lift and shift this to another cloud provider if we wanted to. Running on Kubernetes itself also gives us some performance benefits. So on EMR, obviously you need one node per executor, one node per driver. I believe there's also another node to run other services that you spin up with EMR, such as Ganglia or HBase or anything else like that you might want to run. On Kubernetes, we can spin up larger nodes and bin pack Spark pods onto nodes, so we can reduce the amount of wastage on the node. We also have a extensive observability setup with Datadog on Kubernetes already. So just by running Spark pods on Kubernetes, we get a lot of container metrics for free that would be harder to get when running with EMR. And we've also noticed much quicker scaling on Kubernetes compared to EMR. So on Kubernetes, we use the cluster autoscaler right now. So if you spin up pods on Kubernetes, you need nodes, instances from EC2 to run that behind the scenes. We use a component called cluster autoscaler right now to do that. It typically takes about, if you spawn a new Spark job and there's no instance to run it on, it typically takes about 1 to 2 minutes to grab the EC2 instance to run those nodes on. Obviously, you're still running on Kubernetes. You have to wait for your Docker images to pull with your Spark runtime and your package dependencies and your application. But we've noticed, if from submitting a new job to running it from no nodes, it can take 2 to 3 minutes versus, for example, 5, 10, or even 15 on EMR in some cases. We also can leverage a different resource enforcement framework. On EMR, I believe right now that would probably involve either sharing a cluster or configuring some type of IAM policy based on the attributes of the cluster. On Kubernetes, because you have that consistent interface, we can, maybe not with a consistent interface, but we can leverage a different Kubernetes scheduler to enforce resource quotas in a more declarative fashion. So I'll dive into Unicorn a bit more on the next slide. But when you run Spark applications on Kubernetes by default, you don't get a very good resource quota framework. The Spark operator provides some functionality to do resource enforcement out of the box. So you could define a namespace quota in Kubernetes, and Spark operator will try and respect this when you create applications. But you can end up with problems with like deadlock. So if you submit multiple applications at once, those applications could consume partial resources from each other, and you end up in a spot where jobs are starved of resources across the board. Like jobs can't get their minimum resources needed to run. So I'll explain a bit more on the next slide, but we've used Unicorn to kind of schedule pods on Kubernetes in an application fashion, which I believe is referred to as gang scheduling. So here's the architecture for our Spark on Kubernetes setup so far. So the interface for end users, I guess our teams are experienced in working with Kubernetes to begin with, because all of our other services across the company are Kubernetes. So once we deployed the Spark operator on the K8s cluster, the interface for other teams is the custom resource. So just jumping back to this definition here, this would be similar to what you would submit on EMR, right? When you spin up your cluster or add your step, you will, in Kubernetes, you will create a custom resource and you will tell the Spark operator what you want that custom resource to look like, and that will be translated to the containers under the hood. So in this case, we're saying here, this is just an example that I pulled from the operator repo, but this is an example here of one driver with 0.5 gig of memory and 1 core, and 1 executor with the same resource profile. And it's just running the example PySpark calculate Py example. So if I'm an end user and I want to run that particular Spark job on Kubernetes, I would create that CR. So I would talk to the Kubernetes control plane and I would create that CR, and then the operator would watch that, well, take that CR and create the Spark pods necessary to run on Kubernetes. So that would spin up the driver container, and then in turn, the driver container would spin up the executed containers needed. So it's similar to how it would run on EMR, but it's obviously just running Kubernetes to do it. So creating a CR on Kubernetes requires control plane access, which is obviously quite a privileged access level. Usually that would be reserved for just your CI pipelines. If teams want to create Spark jobs on demand, that requires control plane access from a non-CI environment potentially. So one component that we've deployed alongside the Spark operator is a gateway, which is basically an internal API that services across the company can submit, similar to what you would have from an EMR spec, right? You'd basically this YAML spec but translated into JSON. And then the gateway would take this and create the CR from it. That internal API will be authorized. It'll be matched to teams and accounts. So you can't just have willy-nilly spinning up Spark applications across the company. This will be, it's safer than providing control plane access to all teams, because if we expose the control plane to teams from like non-CI environments, people can spin up any container they like, and that presents a security vulnerability to our cluster. So the other services that we've deployed as well is obviously Unicorn. So Unicorn is an alternative to the K8s default scheduler that implements a queuing mechanism, basically. So like you might, when you submit to, I haven't worked with like Spark clusters directly in a little bit, like as in like submitting from like a shared cluster. I mean, I haven't worked with shared Spark clusters in a little while, but if you wanted to accomplish the same type of queuing functionality, I believe you'd have to use Yarn and configure Yarn to allow that submission. Because on Kubernetes, like I said before, most teams will be using job clusters. We need a separate scheduler that respects basically like a job queue. This is effectively a way to implement job queues in Kubernetes. We evaluated a couple of different schedulers or a couple of different components to do this like queuing functionality in Kubernetes. I think we initially looked at Volcano, but it looked overly complicated for our use case. It seems much more optimized for running kind of fixed size clusters and like and priority sorting applications within clusters. Kind of more like I think some of the code in Volcano seemed specifically around kind of like ML clusters. For our Spark use case, we really just wanted a queue. We're not doing preemption. We're not doing priority sorting right now. We just want, I submit a job. I want it to wait until the resources become available. I want it to get its minimum resources, which is what Unicorn provides. So Unicorn allows you to specify queues. We've taken initially a queue per team approach right now. So teams will get a quota of CPU and memory. They will submit their applications, and Unicorn will only allow applications to run under this limit, and it will queue applications until those resources become available. Other components that we've deployed just to meet the team requirements, we've deployed a standalone Spark history server. So all Spark jobs will write their event logs to a shared S3 bucket that the history server is pointing towards. So we can replicate that same history server functionality from EMR. And we've also deployed a simple metrics transformer component. So Unicorn provides an endpoint to scrape queue metrics. So this is in regards to setting up like Datadog dashboards around queue usage. Out of the box, the Unicorn metrics aren't in the right format to easily set that up with tags on Datadog. So we've just built a simple little application to scrape those metrics and transform them so teams can view how much of their queue that they're using. We can get the same thing from the platform side as well. So I've already referred to a couple of these from the previous slide, but just to talk about some of the issues that we've encountered and how we've solved them. External control plane access to actually create the Spark application CRs. We've started with an existing open source gateway from Apple. I believe Apple's done a KubeCon talk on this already. If you look at the repo, there are some links to 2 talks that talk about this gateway already. They provide a lot of information that served as the basis for us implementing Spark on Kubernetes. But we started with this to save it building ourselves from scratch. But we've also modified it and built it along the way because it doesn't fully meet our needs internally. We've also had to modify the Spark operator as well to support the gang scheduling with Unicorn. So the Spark operator supports gang scheduling with Volcano, but it doesn't. It provides an interface to create a little plugin to say, I have a Spark application, I want it to be scheduled with Volcano. You can specify that, and there's a plugin already in the operator that does that. We've had to implement the same thing for Unicorn, because otherwise, when you submit the application, Unicorn needs certain information about how to accomplish the gang scheduling. So we've implemented a custom plugin in the operator that adds that information. We've also had several issues just operating the Spark operator in general. So to replicate the driver UI that you would get on EMR, previously we spun up a load balancer per driver and set that to an internally accessible hostname. So you could go to your driver UI via an internal address. Spinning up a load balancer per driver pod is obviously expensive, but it also caused issues with the operator itself. So the operator expects all resources of the application to be cleaned up within a certain period of time. Load balancers can take, we noticed from AWS's side, load balancers can take up to 30 seconds to clean up. So this caused some applications to become stuck if the load balancer took too long to clean up. This was a particular pain point for teams that deployed streaming applications that sometimes just died due to out-of-memory errors. When those applications were rerun by the Spark operator, sometimes they weren't resubmitted because of this issue. So this was a particular pain point to solve for teams that are using the Spark operator. And when we just do regular Spark operator deployments using Helm as well, we've noticed some downtime. So I didn't go into too much detail about how the Spark operator itself works, but the Spark operator relies on a controller and a webhook available. If you're not familiar with Kubernetes, I mean, webhook is like a broad term, but if you're not familiar with Kubernetes, basically the controller controls how the application is submitted on Kubernetes, and the webhook adds some details into the application. But the main point is that those two components needed to be up at all times to utilize all features of running Spark on K8s. And during deployments, with the way that the Helm chart was configured out of the box with the open source version, it caused some downtime during those Helm upgrades. So because we run a lot of streaming applications on Kubernetes that go through executors, like they scale up and scale down quite quickly. So there's a lot of executor churn on those jobs on Kubernetes right now. We noticed our deployments from the platform side were quite noisy. It was causing like delays, and it was causing downtime for the client teams basically. So we've had to modify the Helm chart and some of the operator code to basically ensure zero downtime deployments from our side. We have made some other modifications to the Spark operator as well internally that we would like to upstream, but we're a little bit concerned about the upstream ownership of the Spark operator. But that's something that we will, continue to support internally. We'll continue to support the version of the Spark operator we've got internally. We've also noticed from just running on Kubernetes, you obviously have to tolerate some node replacements. You can't just assume that your container is going to run on the same host all the time. So this is something that we're working through at the moment. So streaming applications, if a team deploys a Spark application on our setup, I guess the expectation is that their application may need to be restarted occasionally if we need to swap the underlying hosts that those pods are running on. So those applications will just be resubmitted and rerun on another host. But long-running batch applications, especially ones that run for 6 to 12 hours that might not have incremental, like they might not just be able to be restarted and picked back up. We need to be careful around how we do node replacements with long-running batch applications at the moment. Solution for this is still kind of work in progress, but we'll probably just, time out the node replacements basically. So we don't replace nodes on long-running jobs. We will wait for those jobs to complete before we replace the nodes, or they will only be scheduled on a new node, or the old node that they're running on will only be taken away once that job is complete. Obviously on EMR, you don't have to think about a lot of stuff because EMR, runs the operator or runs Spark behind the hood. They don't reclaim your EC2 instances usually, so you don't have to think about that stuff in an EMR environment. So there are some differences between just running Spark on EMR, where you can expect a fairly stable platform, versus running on Kubernetes, where with a stateless service, you kind of just take for granted because pods just shift around. Once you start running with state on Kubernetes, you need to be quite careful about replacing underlying hosts. And just another small thing as well, because we've deployed a lot of components on the platform, obviously we can only test so much, with unit tests and things. So we've implemented a kind of end-to-end smoke test basically that runs on a schedule just to make sure to verify that our platform works end-to-end. Talk about the results of how the migration has gone. So we have about 25 applications running in production right now. I don't know how many applications run across, 500, I guess I mentioned it earlier. So we're not running a whole lot of applications on Spark and Kubernetes right now, but they are ones that have been running in production for a while. So as you can see from our kind of number of pods running chart, that's been slowly increasing over time. The platform has been stable enough lately, and we're planning to migrate more workloads onto Spark and Kubernetes as time goes along. The infrastructure setup is still a work in progress, and there's obviously still more applications to migrate. And in particular, the challenge will be those larger batch jobs. So there are some Spark jobs at Rokt that spin up a really large Spark cluster and run for quite a large period of time. So those applications in particular will probably put a lot of load on the cluster. I think in general, running large pods on Kubernetes isn't a concern. Like if you spin up a pod that requires a terabyte of memory, if you can get an underlying host that has a terabyte of memory, that's not the problem. The problem is when you spin up 2,000 pods and you need 2,000 hosts. Once you start getting lots of pods and lots of hosts, you will have, you need to watch just the general health of the cluster in terms of like how the cluster is performing at the scheduler, how are your storage provisioners performing. So that's something we'll keep an eye on. I'll touch on the next slide, but that's something we'll keep an eye on as we onboard more applications. In terms of some of the benefits that teams have seen so far, in particular, some teams have taken much more use of dynamic allocation to scale up their jobs when there is work. So we have some streaming jobs where it's not a consistent workload coming in. So these jobs can have much more aggressive dynamic allocation timeouts. So Spark will scale the number of executors up and down more aggressively because on Kubernetes because the scale up time is shorter, those teams can enable that, which reduces the amount of idle time that there is on the Spark job. Obviously, we're saving 10 to 20% because we're not paying for the EMR markup. Because of our container metrics, data log observability, we get an increased visibility that was not really visible before. You would have had to look into Ganglia for that. Now we can have dashboards across multiple jobs, so it's easier to spot idle executors. It's easier to spot teams that are over provisioning, and Unicorn as well. Unicorn. When I said that Unicorn was kind of a bit simpler than Volcano, Unicorn's a bit simpler out of the box, but it does provide ways to implement priority queues, for example. So if we had an AWS incident, right, and there's issues getting new EC2 instances, if you're using EMR, you'll just notice that across all of your jobs. Because we're running on Kubernetes now, because we control the way that we control the allocation of the Spark jobs to the compute, we can now prioritize certain critical workloads across the company. So if there's an EC2 incident, for example, we can prioritize that our business critical applications will run ahead of jobs that can tolerate some downtime. So in the future, we're going to reduce node wastage. So at the moment, we're just using cluster autoscaler to get the nodes behind the scenes. So again, if you're not familiar with Kubernetes cluster autoscaler, you have to basically configure one EC2 instance type that you use, or potentially multiple, but you need to pick the EC2 instance type that your containers will run on. So at the moment, we've kind of over-provisioned the nodes to make sure we can fit all the pods at the moment. So over time, we will look to more efficiently match the nodes that we get to the jobs that are actually running on the cluster. And in particular, we might look at using Carpenter to grab a pool of nodes to effectively reduce the difference between what the containers request and what the underlying host has. So Carpenter, if you're not familiar, basically fetches instances from EC2 that match the pod. So if you have a pod that wants 2 CPU and 4 gigs of memory, it will fetch an EC2 instance that matches that profile. So you can reduce the wastage on the node. We're going to investigate. We haven't done much investigation into this for now because we're still just migrating jobs onto K8s, but we're going to investigate whether scheduling multiple Spark pods on the same host can cause any noisy neighbor issues. So Kubernetes can share CPU and memory pretty efficiently. So as long as the containers have limits, the CPU and the memory can be pretty efficiently shared. But we, in particular, want to check if there's any I/O or network degradation from sharing the host versus having a dedicated host like you would on EMR. We also want to keep an eye on the control plane and system component latency. So like I mentioned, if you have more pods on Kubernetes, the scheduler, the control plane, I guess that's EKS behind the scenes, right? EKS will just come under more load. So we need to just monitor the general cluster health. But we're confident that a single cluster approach will hold up for a while because we run another cluster with quite a lot of load, and that's been holding up for a while. So we're not concerned at the moment about spinning up multiple clusters, but this may be something we need to do in the future once more workloads are migrated across the company. We're also going to look at running Spark on ARM nodes, just so we can, on AWS, for example, we can run on Graviton and save a bit of money. There are some use cases as well for EMR notebooks, EMR Studio across the company. So to avoid the same vendor lock-in cloud agnostic approach, we might look at providing a notebook experience using Jupyter Hub. Our team has a vision to provide like a more general data, I guess like a data experience across the company. So obviously not everyone wants to use Spark. We will probably in the future at some point look at supporting Flink as well within this same kind of Kubernetes experience. And same thing, we might look at also providing a workflow scheduler like Airflow or Flight. At the moment, those kind of workflow runners are managed by separate teams that might all at some point come under centralized. And we can provide kind of, if you want to run a Spark job, you want to run it on a cron job, here's the technology you use, here's how you deploy it. And that's all kind of our components that we manage. So, teams aren't deploying their own Spark operator, teams aren't deploying their own Flink operator. That will kind of be a managed experience from us, I guess. And that's it. Thank you.